What's wrong? Okay, 29 copied twice. But I have 29 and this is a 39. Oh, that's because there is, first I read it as a 2 and then I read it as a 3. Okay, 62 comes back. Okay, so this is a 29 and this is a 31 and this is a 62. Okay, good. Sorry about that. No, it was my bad. It was your good because it just this extra little bit here where I erased it and then wrote it again, it made me think it was a 3 because I was reading it quickly. Never mind. Sorry. No, thank you. Well spotted. I used to throw candies at the class, except they didn't like the candies anyway. But now I can't do that either. So the point of this is notice that here when I merge 31 and 45 into 76, so every element of this list of size 31, it participates in every merge all the way to the root. Okay? So that means that this time, I can think of this as, instead of 76, I can think of it as 31 plus 45. Sorry, that should be an internal one, it should be a circle. Okay, and then it's 76 plus 29 is 96, is 105. And then 145. And then over here, this is going to be 23 plus this, 60, 122, 145. You don't have to be able to read this. 122, 265, 267. Okay, 267. So notice that 31, every one of these 31 participates here, 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 and here. So it's 1, 2, 3, 4. That's exactly the depth, because you measure the depth in the tree by the number of leaves, number of edges to get from the root to that leaf, which is 1, 2, 3, 4, right? So actually, the total cost of these merges is 260. The 267, but this is I pay for every one of these 31, I pay for it here, I pay for it here, I pay for it here, I pay for it here. So it's actually the total cost of this tree is the sum of the sum over the leaves, sum over I of Wi times di, where Wi is the weight of the leaf and di is its depth. Okay? So that just helps you sort of formalize this notion of what you're trying to do. You're trying to find the tree that minimizes that. Okay? People are happy? Sorry about that, messing up with the 29 and 39. Okay, so is this a good tree? No. This is a silly tree. Because if I'm trying to minimize the, maybe you can't actually see this tree easily with the webcam, but if I'm trying to minimize this, why would I put 29 higher than 45? Right? Because that way I'm paying 45 more times. Right? Every element of this 45 is participating in more merges. So actually, what I can do is say, I can take a lighter, higher leaf, like 29, and swap it. Okay, actually that's not right. So if you go on and you're writing academic papers, you don't write I, you write we. To the extent that one of my friends once said that she was reading a paper. So even if you're writing a single author paper, you write "we." And she said it was really weird because she got to the acknowledgements and the author had written, "We thank our wife." Okay, we can take a lighter, higher note and swap it. And this is supposed to make you feel included. Okay, actually, before we go on, I'm going to make you do this. Okay, so random choice. Now the problem is maybe. Okay. Does anyone want to volunteer and tell me what the next words are going to be? Oh look, there are people who have their pictures. Nobody's going to volunteer? Yes. Okay, with a heavier, deeper. Okay, lower, higher, lower. Okay, deeper, lower. Let's say deeper, because lower, then you think about lower cost. Okay, deeper. Okay? Without increasing the cost. Okay? And the other thing is, you can take two leaves at the same depth and swap them without changing the cost of the tree. Oh, there are, yes, okay. No, you don't have to use tree rotations here. You just grab them and rip them off and glue them back on. Don't worry about the data structure at the moment. Oh, while I was asking you that question, I could have taken a drink of my tea. Oh, my mouth is so dry. Okay, so, chai. We can swap two leaves at the same depth without changing the cost. Okay, so why does this get Alan off the hook? Why does Alan not have to worry about, is this still recording? Maybe it's still recording the whole board. When I turn the record on, it seems to, well, it's printing the length of the video, so it shrinks the screen. So I hope it's still recording everything. Why does this get Alan off the hook? Because suppose somebody gives us, okay, so this is, somebody gives us a tree, maybe like this one. But there is, yeah, so remember, Alan said merge 23 and 29. So let's suppose there is a tree like this. There is some tree T sub opt, some optimal tree. Okay? And in this tree, it's going to have, make this a bit bigger, 23 somewhere, and 29 somewhere as leaves. Okay, but what we want to show is that there exists an optimal tree in which Alan didn't mess up. Okay? Alan said merge 23 and... I'm sorry, Alan, if you're like, don't worry. This is... I can use... I mean, okay, don't worry. You got it right. I don't know. Maybe people are never going to answer questions again. No, okay. Maybe. I hope. So Alan said take 23 and 29. So maybe in this optimal tree, some people may have seen this before, so I'm not going to answer that question. If you've seen it before, don't say anything because I want it to be a surprise for some people. Okay, you take 23 and 29, but actually you don't have to worry about that. Alan, you just have to care about, did you get this first step right? And then yes, by the induction, if you got the step right, then you're like, yeah, okay, so then it works for the rest of the algorithm, because remember when you merged it into 52, I said you forget that the 23 was there and the 29 was there, and you just keep going as if this was your original set of lists, collection of lists. So we have this t-opt, and then you think, so how can you take this and say, well, if this t-opt, this tree is optimal, there exists some tree in which 23 and 29, Alan said merge them. So that means in a tree according to Alan, they're siblings. Okay? Well, remember, we observed that you can take a lighter, higher leaf and swap it with a heavier, deeper leaf without increasing the cost. Alan chose 23 and 29 because they are the lightest leaves. So we can take 23 and 29, or 29 and 23, doesn't matter about the order, and we can take whatever leaves are deeper, whichever the deepest leaves here, remember it's a strict binary tree, so you can't have a single leaf which is deepest, because it has to have a sibling. Unless, except for the case where you give me only one list and it's sorted, in which case my tree is only one node, but then why am I doing this anyway? Because I have one list. Okay, so you can take them and swap them. So now they're at the deepest level. But maybe they're not siblings, like Alan wants them to be. But we can take two leaves at the same level and swap them without changing the cost. So now we can take 23 and 29 and we can put them beside each other. And now we didn't increase the cost by moving 23 and 29 by swapping them with the deepest leaves, and we didn't increase the cost by moving them together and putting them beside each other and making them siblings. So this tree, T sub Alan, is also optimal. Okay? So that means that after Alan has done that first step, there exists, then you take this node, which is going to be now drawn bigger, and has weight 52, so now Alan can say, okay, now this tree looks like this, these two go away, now there has to be some merging procedure on the other lists and this new list of length 52 that is optimal. But is that Alan's problem, how that works? How you merge the rest of this? No. I didn't say you have to give me the whole merging procedure. I just said, what is the first step? So Alan is safe because the first step is not a screw-up. After that step, there exists a way to keep merging and get an optimal solution. Okay, now then you say, by induction, well, if you give me a single sorted list, this works. If you give me L sorted lists, then I take a step, I get L minus 1 sorted list. Suppose that this works on, okay, so induction is, suppose it works on up to L list. So suppose it works on 1 list to L minus 1 lists. Then this greedy algorithm of merging the cheapest leaves, it also works on L lists. So by induction, we're done. Okay? We solved the warm-up exercise. And it took us only, I have half an hour left to tell you about Huffman's algorithm and how that works. Don't worry, I think I can do it. We may not get into like canonical Huffman trees and canonical code, but don't worry, I think I can do it. We may skip von Leubn's algorithm, but nobody teaches that in undergrad anyway. Okay, are there any questions about this warm-up exercise? Does everybody get this? I can safely put this on the exam. Hands up. Wow. Okay. Fantastic. So everyone sees how to, well, 3 people at least, everyone sort of sees why, intuitively, why you would take the 2 smallest lists and merge those first. And now people can sort of see the argument for how you prove that this is optimal. Don't worry, you're going to get a lot of practice. You're going to hear these words. Suppose that after I steps there exists an optimal solution S that extends your sub-solution. Then show that we show that after I plus 1 steps there exists an optimal solution S prime that extends our sub-solution after I plus 1 steps. Okay, you will hear that ad nauseum. That's basically what we're doing here. Okay, now I'm going to tell you about prefix coding. So what happens? Has anyone ever learned Morse code? No. Okay. So normally, I forgot to prepare this. Yeah, forget this. Don't forget it. Keep it in the back of your mind. But I need the board space. We move on to prefix coding. So what happened? What is this problem? So suppose that we have a random variable x which takes on some values. For example, x could take some values in the set. So maybe X is my Christmas present, okay? So my Christmas present is there under the tree, and it's in a box, and it's wrapped up, and I'm trying to think what it is, and I'm going to open the present, and I'm going to get some information. And what could my Christmas present be? It could be kitten, gloves, webcam, I don't know, like coal, I don't know, I don't actually get Christmas presents. I don't know, what do people get for, maybe it's not a Christmas present, it's just some random gift. I open I know, it could be, I'm ordering groceries and I just click fruit box, like I click veggie box, and it comes, and there are things in there that I don't know what they are, so I have to use Google image search. And so last week I got a celeriac and a kohlrabi, and I've never seen these things before. So let's say X takes on values in the set. Turnip, celeriac, kohlrabi, potato, blah, blah. Okay. So you see, so there's some random variable takes on these values. Until you open the box, you don't know what's in there. It's like this box of chocolates, right? Okay. According to a probability distribution, P1 to Pn. Okay? So, what you want, if you think, so it's called a prefix-free code, it's also called an instantaneous code, which means that when you get to the end of the code word, you know what code word was sent. So, okay, what's going to happen is, Yang B, you were the last person to raise your hand, or give me a thumbs up, so I'm going to be sending you a message about what vegetable I received in my veggie box this week. So we're going to have discussed this code. We're going to have chosen a code, a prefix-free code, so that I can send you as few bits as possible to tell you from now on, each week I send you a code word, and you will know which vegetable I have received. And we want to minimize the expected number of bits. So, okay, we will assign a code word to each vegetable, and we will do this such that the likely vegetables, like potato, the vegetables I think are likely, I got more potatoes in the box than kohlrabi. I only got one kohlrabi. And I've never seen a kohlrabi before. So maybe I have. I just didn't recognize it. So, this is not like ASCII where everything is 8 bits. We want to make the frequent things have short code words and the infrequent things have long code words. But the thing is, we want it so that you can stop listening to I'm going to send this by Morse code over our telegraph or something like this. I mean, this is because we can't meet and maybe my internet is broken. I'm going to do it with a flashlight or something, you can people. I never actually did this when I was a kid, but I knew people who would try to send messages between houses with their flashlight. I've seen it in movies, I think. Okay, so once you get to the end of the code word, you can stop watching. Okay, so we don't want it, so the code word for potato is a prefix of the code word for kohlrabi, because then I'm short, long, and you think, oh, potato, and you turn and go away, and then long, short. Okay, that was the code word for kohlrabi. You don't want it to be dot, dash, short, long is potato, and short, long, short, or something is kohlrabi. Now actually, if you look at Morse code, they do actually have this because they also have, you have to listen, you have the interword and inter symbol spaces that disambiguate this. Forget that for now, okay? This is bad because after you see short, long, you're like, yeah, okay, no, that was a potato, and you start doing something else. So we don't want it that, we want every code word, we want the set of code words to be prefix-free. No code word is a prefix of any other code word, okay? So, the problem is, come up with a set of code words. People are still here, right? People haven't given up. We still have 40 people. Come up with a set of code words such that the expected code word length is minimized. Okay? Now, Shannon came up, he defined the entropy of this random variable, which is a function of the probability distribution P1 through Pn. And he showed that was a lower bound on the expected code word length for any prefix-free code. And then there were the Kraft and McMillan and Cannon, they showed that actually it's for any unambiguous code, even if it's not prefix-free, blah, blah, blah. You don't have to know about that. And then there was this open question that got Hoffman out of his exam and made him famous and widely cited and got him tenure and all kinds of stuff. So, if I give you the probability distribution P1 to Pn, what do you do? What's the first step? So somebody put their hand up if you know the answer and you haven't seen this before. You don't already know Wolfman's algorithm. Okay? So I told you, Shannon was a first-class genius and he didn't see this. Now, we have a lot of tools and a lot of background and for algorithmic development, we know a lot of tricks. People were, like computer science was still young back then. Okay, well let's think about it. A prefix-free code, so it's a binary prefix-free code, so zeros or ones. So remember, if you saw it in the last lecture I was drawing trees, and so actually if anybody had learned Morse code, they actually teach Morse code by saying it's you teach it as a tree. So suppose that I have a code that's, well actually I'm going to draw a tree first. How many? 1, 2, 3 potato, and what's a couple more things? Tomato is actually a fruit, but we're going to ignore that. Tomato, cabbage. Help, I need another vegetable. Somebody. Yang Di? Vegetable? Some carrot. Carrot! Carrot, carrot. People like carrots. Okay, carrot. So, 1, 2, 3, 4, 5, 6, 7. Ah, the same as before. Okay, so let's suppose okay, so this is carrot, turnip, celery, kohlrabi, potato, tomato, and cabbage. Okay? So, the code word for carrot is 0, 0, 0, 0, 0. Why, if I draw this as a tree, why do you know that that no code word is a prefix of any other code word? Because the code word for a vegetable is the concatenation of the labels of the edges on the path to that vegetable. So if any code word was a prefix, then it would mean that the label for that vegetable would have to be in the middle of a path to one of the other vegetables, which would mean that it wouldn't be a leaf. So as long as I label the leaves with the vegetables, then if I take the 1, 2, 3, 4, 5, 1, 2, 3, yeah, okay. Carrot, 0, 0, 0, 0, 0. Turnip, 0, 0, 0, 0, 1. Celery, 1, 2, 3, 1, 1.
Professor, I have some question if you answer.
Wait, why are cabbage and celery connected?